Hello, welcome to the fourth session. Okay, so the first talk will be given by Srinivas. It's about a paper by Jean-Sébastien Coron entitled Higher Order Conversion from Boolean to Arithmetic Masking. Thank you, Srinivas, for giving the talk.
Thank you, Emmanuel, for the introduction. So it's full screen. As Emmanuel mentioned, I'll be presenting on behalf of the author Jean-Sébastien Coron, who could not make it to the event due to personal reasons. So I'll try my best to answer the questions. So in case you punch me hard with questions, then I'll kindly transfer them to the author. We all know that side channel attacks are a practical threat to cryptographic implementations. In particular, differential power analysis attacks, they are one of the most powerful forms of side channel attacks. And masking is a popular and effective countermeasure against DPA attacks. So the basic idea behind masking is to randomly split a secret into, say, two shares, such that the XOR of the shares is the original secret. So now, because the two shares are individually random and independent of the secret, so that means that so it will not leave each of the shares do not leak any information about the original secret. So now, how to compute in the presence of shares? The linear operations, they are quite straightforward. Just we need to apply the function on each of the shares and then combine the outputs. So the main challenge is to mask the nonlinear operations. So for a block cipher, it would SPN block cipher, it would reduce to masking the S box. One of the very first countermeasures to mask an S box is the randomized table method by Chari and others. So far, like in the example, what was discussed was the Boolean masking, but some algorithms, for example, the ciphers IDEA or RC6 or SPEC or even SHA-1, they require arithmetic operations. So in these cases, it makes sense to also use the arithmetic masking due to efficiency. Suppose the secret, for instance, it could be an input to the S box in some round of the block cipher operation. So suppose X is a k-bit string. So then we want to find two arithmetic mass such that the modular sum, modulo 2 power k, the sum is the given secret. So now this arises the question, the problem, like if we have a Boolean shares for a secret, then how to convert them to, how to find the corresponding arithmetic shares for the same secret. The very first solution was given by Guba at CHES 2001. So he proposed a first order secure Boolean to arithmetic mask conversion algorithm, and also in the opposite direction. So that was that algorithm, conversion algorithm by Guba is secure against first order, but we all know that second order attacks are feasible. So basically, here in a second order attack, an adversary can exploit simultaneously leakage from two leakage points. It requires more curves, but still it's been demonstrated to be feasible. So what's the solution? So just use n shares where instead of 2 shares where n is greater than 2. So what we would desire is any subset of n minus 1 shares should be uniform, random, and independent of the original secret. So that means that the algorithm is secure against a DPA attack of order n minus 1. So with n shares, n minus 1 is like the optimal security what we can achieve. Quite often it turns out in practice that one can only achieve security of less than n minus n with using n shares. So in Boolean masking, an secret variable is split into n share such that the XOR is the secret X. And in arithmetic masking, we have n arithmetic shares such that the modular sum is the same secret. So now, how do we convert between Boolean and from Boolean to arithmetic masking when there are more than 2 shares? So the author in this talk, the author's contribution is an efficient and probably secure higher order conversion algorithm from Boolean to arithmetic masking. So some of the works in this direction are as follows. So here n denotes the number of shares and k the size of the register, and all the arithmetic addition is performed modulo 2 power k. So for instance, k is equal to 32 for HMAC SHA-1. As I mentioned before, the first algorithm for this conversion is by Guba from CHES 2001. The complexity here, by complexity, what it specifies is the operation count. So an XOR of k-bit words or an modular addition or a random sampling of a k-bit word is assumed to take a unit operation. So with this assumption, the Guba's algorithm from Boolean to arithmetic mask conversion has constant complexity, while from arithmetic to Boolean, it has complexity order of k. Again, k is the size of the words, register size, for instance. So then this Coron, Groschadel, and Vadnala at CHES 14, they proposed higher order Boolean to arithmetic as well as arithmetic to Boolean conversion algorithm that works for any arbitrary number of shares, and its complexity is order of n square k. The same authors along with Tibuchi at CHES 15, they improved this complexity to order of n square log k. So what the author of this work proposes is a Boolean to arithmetic conversion algorithm of complexity order of 2 power n. So note that this complexity is independent of the register size. So as in Guba's first order algorithm. Though it's of exponential complexity, but for small values of n, it turns out to be 1 order of magnitude faster than the prior work. So here's the plot of the operation count of the proposed algorithm with that from CHES 14. So here, so we can see that for small orders, it's it's much it consumes much less operations, and we see that this is the security order. So when there are about 11 shares, so then it equals and then it surpasses the CHES 14 method. So we will see the concrete timings towards the end of this talk. So what has been proposed is a conversion algorithm from Boolean to arithmetic masking that works at any arbitrary order, and with a proof of security in the probing model of Ishai, Saha, and Wagner from Crypto 2003. So the proposed algorithm is a variant of an algorithm that was very recently proposed by Hutter and Tunstall, and it was put up on ePrint archive. Hutter and Tunstall's method did not come with security proof at arbitrary orders, and the author proposes a third order attack that works for any number of shares. We will not discuss the details of this attack in this talk, and I kindly refer to the paper for the details. So just let us recollect the security model of Ishai, Saha, and Wagner, the probing model. So assume we want to securely evaluate a block cipher that takes an input message M, and with the keys, say the n shares of the secret key. So then we allow the adversary to say probe T intermediate variables. So in order to prove the whole operation is secure against some say the Tth order attack, so we just need to construct a simulator that has access only to a subset of the shares. So if we can simulate the leakage on the probes using only a subset of the shares, so this means that the adversary will not learn anything, because the adversary himself can simulate the subset of the shares just by picking uniform, random, and independent values. Piece of advice from the author is that never publish a higher order masking scheme without a proof of security. So because at higher orders, things can go wrong in many ways, then we can possibly get it right. And we have already seen many countermeasures in the past without proofs being broken. So it looks like that we at a higher order we have still have only a poor intuition about the security. So before we describe the proposed Boolean to arithmetic conversion algorithm, let's recall the Goudarzi algorithm for first order. So Goudarzi algorithm is based on a surprising fact that the function psi that takes two k-bit strings, XORs them, and modular subtracts the second argument. So this function turns out to be affine with respect to the field of two elements. So using this fact, then it's straightforward to come up with a conversion algorithm. Suppose there are two Boolean shares of a secret x1 and x2. Then just need to subtract modular subtract x2 and then add x2 as suggested. And then from the definition of the function psi, then we can write like this. And then using the affine property of psi, we can finally write like this, and we get two arithmetic shares, A and x2. And in the process, like every intermediate variable is independent of the secrets, so hence it's first order secure. So what the proposed algorithm of the author is a generalization of the first order algorithm by Goudarzi. So here we instead of two shares, we have n shares. So then so just subtract and modular subtract and add XOR of all but the first share, and then again from the definition of the same function psi, so we can write like this. And thanks to the affine property, this follows. And then we end up with sum of XOR of the Z shares, n-1 shares, again, the XOR of n-1 X shares. So then the idea is to recursively apply this trick, and finally we get n-1 shares A and n-1 shares B, but we want n shares. So just for that, just group every pair except the last pair, and we get finally get n arithmetic shares. So in order for this algorithm to be secure, a key component is the mass refresh algorithm. So the share should be continuously refreshed, otherwise it would lead to an attack. So so using the strong non-interference and strong non-interference definitions introduced recently by Barth and others. So I will not get into details. So I just would like to mention that these security notions would enable a modular security proof. We just should analyze each gadget separately and then argue about the security of the composition. So the proof can be found in the longer version on the ePrint archive. So here's the concrete count, and again we see that for low orders it's 1 order of magnitude faster than the previous CHES 14 work. So to conclude, what the author proposes is a higher order Boolean to arithmetic conversion algorithm, and it's an extension of the Guba's first order algorithm, and it's probably secure in the probing model. So the complexity is order of 2 power n for n shares, and it's independent of the register size. Still, it's worse than the CHES 14 method that has a complexity order of n square times k, but it is 1 order of magnitude faster for small n. So the obvious question is, like, can we do better than order of 2 power n? Yeah, thanks for your attention.
Thank you, Srinivas. Because Srinivas is not one of the authors, and because the author is not here, I propose that you send directly your questions to Jean-Sébastien, if you're okay. Thank you, please. Thanks, Srinivas again. So the next conversation is about reconciling D+1 masking in hardware and software, and the talk will be given by Hannes Gross.
Thanks. So, thanks for the introduction. So this talk is about the reconciliation of D+1 masking in hardware and software. But before I'm actually going to start my talk with a brief discussion on why we think that it was about time that the hardware and software masking world get together and talk to each other, let me first briefly summarize what we achieved in this talk. So in this work, we had a closer look on the most randomness-efficient hardware and software masking schemes and combined them into what we called the unified masking approach, or in short, UMA. So UMA has some very beneficial practical properties. For example, especially in hardware, it requires only half the randomness over the state of the art. It uses only D+1 shares, which makes hardware implementations very efficient. And it's completely generic in terms of protection order, which means that once we created a design, we can simply synthesize it for any protection order. And since we also target hardware designs, it's of course also glitch resistant. So this sounds nice. How does this map to practical properties? This we analyzed in a hardware case study where we took the authenticated encryption design ASCON as the basis. So we compared the UMA versus the domain-oriented masking scheme on basis of ASCON. The domain-oriented masking scheme was the most randomness efficient masking scheme up to this work and has otherwise quite similar properties. Both our designs are completely configurable, for example, in terms of number of S boxes you want to use. This allows us to compare UMA versus DON for a very small amount of nonlinearity, but also for a very high amount. So we will state results for the protection orders 1 to 15. And as always, both of our designs are available on GitHub to check it out. So I think I already spoiled a lot quite now. So I will save the answer to the maybe most intriguing question, whether or not this randomness reduction pays off, to the very end of this talk. I want to start my actual talk with a brief overview on the history of masking. And as most of the works on side channel protection, I will start with the paper of Kocher et al. So around 1999. Shortly after we became aware of the fact that side channel analysis is indeed a practical problem, also the first countermeasures against DPA arose. Before Quizquarter et al. Showed that the situation is even worse than expected, but we continued working on more efficient masking schemes. And with the introduction of the private circuit scheme or the ISW scheme of Isha et al., we already had a very nice masking scheme that had a lot of very nice properties, like it used D+1 shares, it was fully generic in terms of protection order, so it means it also covers higher order protection and so on. But at some point we discovered that glitches in the hardware, on the hardware side, introduce flaws which produce short moments in time that make the designs attackable. Since this doesn't affect the software world so much, the research in this area continued more or less as before. So there were a lot of papers here, but I'm only going to reference the one that we actually used, which is the Eurocrypt 2016 paper of Belaid et al. And Bart et al.'s bounded moment leakage paper. On the hardware side, on the other hand, the first paper that targeted the glitching issues was the threshold implementation scheme. But right from the beginning, we needed to do a lot of sacrifices in order to cover glitches. But also there we continued working in this direction. So over the time we closed the gap a little to the properties that we already had with ISW. So for example, in the higher order threshold implementation paper of Billion et al., we closed the gap to higher order. In this paper, in the CMS paper of Reparas et al., we closed the gap to D+1 shares. And at the last year's CHES, Vergnaud et al. Presented an AES implementation, and first and second order secure AES implementation with D+1 shares. And at about the same time, we also presented our domain-oriented masking scheme and showed an AES implementation that is generic in terms of protection order and uses the same amount of randomness than ISW. But still, there is a gap that remains between the hardware and the software masking world in terms of randomness. So how big is this gap? As a baseline, I used the lower bound proven by Belaid et al. So we have the protection order here on the x-axis and the randomness requirement on the y-axis. And the best software solutions we have for masking are partially shared by the solutions of Belaid et al. For the first 4 protection orders, and by Bart et al.'s generic algorithm and Belaid et al.'s generic algorithm. So how big is the gap now to hardware, so to the domain-oriented masking scheme? So as you can see here, there's quite a gap. So at some point, this gap even becomes as much as twice the amount as we have in software. But why do we need randomness at all? So therefore, we look at the masked implementation, where at the simplest form that we can have. So we have a one bit multiplication over GF2. And the variables that we use here are really vectors of shares. So A here consists of A0, A1, A2 up to AD, so D+1 shares. And the same is true for B here. And if we want to calculate the multiplication of those two, what we get are D+1 squared terms. And up to now, we don't need any randomness at all. So if we could live with this blow-up in terms of shares here, this would be almost fine. But if we would go on and go into the next nonlinear operation, what will happen? We would need to combine the terms from before, so from A times B, with the first share of C, with the second share, and so on. And in the end, this will produce an exponential blow-up. So this is obviously not what we want to have. And therefore, we need something that we call compression. So we want to take the terms from the multiplication before and compress them again into the minimum amount of shares that we can have, which are D+1 shares. And so we need to add up these terms. But the difficulty here is that none of these terms is really allowed to come together directly. So how can we do this? We need a randomness to wrap up terms into this randomness, and then we can combine them. And the most efficient way how we can do this, or how this can be efficiently done, is really what the masking schemes are all about. So I'm going to introduce Barth et al.'s generic algorithm, which is also the basis for UMA here. So this algorithm starts with a pointwise multiplication of the vectors A and B here. So this is what we call the inner domain shares. And then this algorithm does a repeating sequence to absorb all the shares, all the terms we have from the multiplication. And this sequence here begins with adding a fresh random vector R0. And then we can start to absorb the first term, which is A times B shifted by 1. Again, a pointwise multiplication. And then the second share, which is the mirror term from before. So in this case, we don't shift B, but A. And then we take the same randomness vector as from before, just shifted by 1. And then we can absorb the next terms. And then the next sequence starts again with a new fresh random vector, but it goes on like that until we absorbed all the terms we have. So as it shows, this is not always the most efficient way to do this. So if we look at a very simple example, so for first order protection, and we put this into this algorithm, what we would get is the following. So we would require 2 fresh random shares. On the other hand, we know generic algorithms that only require one fresh random bit here. So as it shows, Barth et al.'s algorithm is very efficient if we absorb 4 terms in a row. So we call this in the following a complete sequence. If we absorb 3 terms, when we are going to call this a pseudo-complete sequence, because we treat it the same way as the complete sequence, so we also use the Barth et al.'s compression algorithm for that. If we only absorb 2 terms, then we call this a half-complete sequence, and for this we will either use the domain-oriented masking compression, or for the case that D is equal to 2, we use Belaid et al.'s optimized solution for that. And finally, if we only absorb 1 term, then we call this an incomplete sequence. So based on what I said, we can start to assemble the UMA algorithm. So this starts with absorbing the inner domain terms. Then we handle all the complete sequences there are, so there could be multiple sequences. And finally, we're treating the last sequence either by using Barth et al.'s algorithm for the pseudo-complete case, Belaid et al.'s solution for the half-complete case where we have the protection order D equals to 2. And for all other cases, we're going to use the domain-oriented masking scheme. We have the solution in software. For bringing it to hardware, we followed the domain-oriented masking scheme. So basically what we did is we split up this multiplication into 5 basic building blocks that all follow the principle of domain-oriented masking. So these are the building blocks that we already had in software before. So all these blocks follow this principle of domain separation. And by doing so, what we can do is we can implement UMA by just generating these blocks and clicking them together, so XORing the results together. And from this, what we get is we have latency that doesn't get worse for protection orders higher than 3, so it constantly stays at 5. For other protection orders, it's lower. So if we now look back to the randomness comparison that we had before, then we see with UMA, we not only close the gap, or maybe we can see, we not only close the gap between hardware and software, but also in 1 out of 4 cases, we improved the randomness consumption even in software. To show to give a practical comparison, we decided on implementing the authenticated encryption design ASCON. ASCON is a 3rd round CISA candidate. It uses a 128-bit key and nonce. it has adjustable rate with 64 or 128 bits. And this is basically how our hardware design looks. So it's actually quite simple. We only have 3 modules: the control FSM, a round counter, and the state. And the state is where all the interesting stuff happens. So all the state transformations. So we have the S-box lookup that is adjustable, also the linear transformation, and so on. And as I said before, the protection is generic, and the S-box is always pipelined. So this brings me already to the first comparison. As it shows in terms of area, the single S-box variant, so that uses only one S-box at a time, for this, UMA and DOM are considerably close together, which is a bit surprising at first. But given the fact that UMA uses less randomness, or almost half the randomness over DOM, it saves a lot of XORs. And given the fact that we can reuse pipelining registers, because we have 5 ANDs in parallel that all have the same, that have partially the same inputs, we can reuse pipelining registers for that. So this brings UMA and DOM quite close together. The thing changes a bit if we consider the 64 S-box variant of this. So here the gap gets a bit higher. Also in terms of throughput, it shows quite a similar picture. So for the single S-box variant, the throughput also looks quite similar. But for the higher order, or for the 64 S-box ASCII implementations, there's a gap between UMA and DOM. So, but didn't we forget something? So in all the numbers I presented before, these never really reflected the amount of randomness we use or the effort that we have in producing these numbers. And actually giving these numbers is a bit difficult, but because it's based on so many assumptions on how you produce this randomness. But nevertheless, I will give an example, and I think the general message should stay the same. So we use, again, ASCON from a different paper of ours as a BRNG. And actually, this is not the worst choice you can do. So ASCON is a quite good BRNG. It produces 64 bits of randomness every 6 cycles. So in average, 10.5 bits per cycle for an overhead of 7.1 kilogate. And as it shows, even for the single S-box variant, the randomness production soon becomes the bottleneck. So for the domain-oriented masking scheme, this means for protection orders higher than 1, we would need to add an additional BRNG just to produce the amount of randomness that we require for staying at this maximum throughput. And for DOM, this is a little more moderate. And if we take these numbers into account, then we see that the UMA is actually less area hungry than domain-oriented masking scheme. So this already brings me to the conclusions. So today I had the pleasure to introduce UMA to you, a masking scheme that can be used in software and hardware likewise. It saves randomness, especially in hardware, but also in software. And we showed a practical case study where we compared UMA versus DOM in hardware on the basis of ASCON. Both designs are completely generic in terms of protection order, are highly customizable, and are also available at GitHub to check out. And yeah. And the most important message here is that randomness reduction really pays off. So sooner or later, randomness will become the bottleneck if we go to higher order security. And by saving randomness, we save area. Or if we take the reverse conclusion, then for the same amount of area, we get a higher throughput there. So, thank you.
Thank you. So we have time for questions. Any question? Yeah.
Can you apply the same technique to CHES?
Sure, why not? You want me to write? Yeah, yeah. Yeah, of course. Yeah, yeah. So everything. Why shouldn't you? So it's completely generic. So we protected one mask AND gate, so you could use it in all implementations.
Can you say something about ASCON S-box?
It's very nice. It's just 5-bit, and it's quite similar to CAT-check. So basically, if we cut off the linear layer from before, or then it's the same.
Same, yes.
Yeah.
Thank you.
Other question? Okay, I have one question. I have one question. For my information, in slide 5, where will you put Ishai-Wagner algorithm in your figure?
Yes. So it's a bit difficult to see because
yeah,
of the
you can use this one. Yeah.
Oh, sorry, it was
I
later, but okay, I can show you there.
Where is ISW in this figure?
Basically, we are in 1 out of 4 cases better. So in every case, so in protection order 5, 9, and so on. So in all cases where the protection order gives you 1 modulus 4.
Yeah, I was speaking about the classical Ishai-Wagner. Is it true that it will be the yellow curve? No.
Oh,
the randomness consumption.
Sorry. Yeah. Okay. Of course. So DOM has the same randomness consumption as ISW, but the inner structure is different. So if you take a closer look at DOM, you will see that it's not the same.
Okay. I have another question in this related to this. Can I say that any improvement on Ishai-Wagner randomness consumption will almost automatically lead to an improvement to the domain-oriented masking? Is it true, or why isn't
it? Depends on where you see the border between those two. So I don't see this as quite similar schemes, if you want to say so. But basically, what is always true is, as if we can implement it in software, we obviously can implement it on hardware, because software is just software running on hardware. So what makes it difficult is where to place the register. So where you know that you can compose these things or split it up into different submodules and then combine it. So this is what it makes a bit difficult. But basically, every improvement that we do in software, we can also do in hardware. So what I'm hoping for, and why I call this paper also a reconciliation of masking in software and hardware. So there's no need that we separate between those two. We just need to think a bit more of glitches when we do the things in software.
Okay.
That's all. Thank you.
And maybe another third and last question. Is the scheme proposed by Belaid and et al. And the scheme proposed by Bart et al. Have been proved in the same for the same model of security, or?
Actually, with the work of Bart et al., they also introduced this bounded moment leakage model, which is quite similar to what gives you what the deprobing model gives you if you take practical reasoning into account, or if you take your knowledge on masking into account. So I would say yes. So from my perspective, yes. Bart et al. Will probably disagree a bit, but
so when we combine Belaid scheme with Bart scheme, we have the security in which model? The model of Belaid et al. Scheme, of Belaid et al. Paper, or we have security in the Bart et al. Paper, the disorder model.
So you have guaranteed security. Guaranteed, hard to give guarantees, but you have security in the probing model. So
even with Bart et al. Scheme, you have security in the probing model It's the same proving model as Belaïd et al.
So there are differences in the formal part there, but I think it's quite similar. So there is some difference they pointed out, but I don't think I can talk about this. But
Okay.
so from my understanding, it's quite similar. So maybe you disagree with that.
Okay. So thank you for your time and your talk. So the next speaker of the session is Joan Daemen, and he's going to present a paper entitled "Changing of the Guards: A Simple and Efficient Method for Achieving Uniformity in Threshold Sharing."
Doesn't work? Yes, thank you. Okay, thank you for the introduction. So I'm going to speak about something old, more like a nostalgic presentation. Let me first give a disclaimer. So I'm in the session on higher order countermeasures. This is not a talk about higher order countermeasures. It's just we're happy with the first order, but we try to do it without randomness. Okay, so modern symmetric crypto means, in my opinion, does this work? Yeah, means permutations. So how would we build a cryptographic permutation? It's like a block cipher without a key, so you can consider it like a block cipher without a key. We repeat a simple round function a number of times, and this is a kind of a circuit schematic where we have here a counter that counts the number of rounds. Let's say we want to do 10 rounds, then we just iterate this 10 times. And every round we add a round constant, so that's how it works. So we can implement this in a simple circuit where this is the round logic and this is the state we work on. Yeah? So initially we give here the input, that goes one time through the round function. And if we done our number of rounds, which is 10 or 16 or 24, we give it to the output. If you have a block cipher, then this is not a simple counter, but this would be the key schedule. And you see more or less the schematic. If this is a block cipher, this would be alternating key cipher, or key alternating cipher. Otherwise, just an iterated permutation. So we reduce the design of this primitive, which is like it has cryptographic properties, to that of a round function. And you can do it in many different ways. You can do combine addition, XOR, and rotation. That would then be an ARX primitive. But the way I prefer is the good old white trail strategy, where you have a nonlinear layer. You have 3 dedicated layers, each one with its own task. A nonlinear layer that I here symbolize by a layer of S boxes. Then a transposition layer that moves elements around. In this case, these are bits. So, for instance, this S box here, every S box takes 3 bits, and the 3 output bits, they go to different positions. And a third layer, which consists of mixing. So here, this is kind of, you can consider this also as S boxes, but that are linear. And the point is that they make sure that every bit depends on multiple bits. So if you know AES, this would be our sub-bytes, that would be our shift rows, and these are mixed columns. And the addition of the round key is here, in between the rounds. Okay. So in the white trail strategy, the original idea, as I originally proposed it, is to have very simple and light, elegant building blocks that achieve a good resistance against linear and differential cryptanalysis. And for the S-box layer, well, the nonlinear layer, which is not necessarily an S-box layer, I had very early in my academic life found something that worked quite nicely, and I called this thing CHES, and some of you may know it. It basically operates on a linear array of bits, so these are bits. I represent a 0 by a white circle, or what is it, a dot, white dot, and I represent 1s by a red one. And how CHES operates, basically, it first tries to identify patterns of 0, 1. So you get here a 0, 1, 0, 1, 0, 1, 0, 1, you see? And then for each of these patterns, we're gonna complement the bit at its left. So, for instance, for this pattern here, we're gonna complement this bit. And for this pattern, this bit, and so on. So if we do that, we get this, see? So it's a very fast mapping, very efficient. And that's it. So that's the nonlinear layer. And you can easily program this. If we put a bit in CPU words, this is the simple operation, basically. We modify a bit by adding, XORing in an expression of the two neighbors, well, this is an AND. We can do multiple of these things together if we put the bits bit-slice fashion in these words. So we can do 8 at a time if these are 8-bit words. More algebraically, we can express the new value of a given bit as its old value plus the sum of its neighbors, the product basically, where one of the two is complemented. It's a very simple expression. You see that this has an algebraic degree too. Yeah? So it turns out that, yes, so I didn't explain where this is going on the right and at the left, but we assume they're put in a circle. So if we arrive here, we get back in here. Yeah? So it has a certain length. And for odd length, this is invertible. Yeah? For even length, this is not invertible. So that's very strange, but yeah. So this is a kind of not so nice, because we cannot really use this for instance, for creating a 4-bit S-box, or for a 6-bit S-box, or 8-bit. But we can do a 3 or 5. Huh? But yeah, in block ciphers, we always like to have here state size of the power of 2, but in permutations we don't need to. Huh? And we will see later a permutation with 384 bits, which is not the power of 2. So basically this nonlinear layer was used in Ketchak-F, the permutation underlying Ketchak, Kiak, and Ketchak. I should also say it's also used in Ascon, so as you learned just now. But it's much older than that. We use it in the predecessor of Ketchak, Radio Gatun, in Panama, which is even older, Base King, which is even more old. We go back to 1992, 3-way, and before that, Subterranean and Cell Hash, that was in 1991. And basically, the first time I described this and the properties of this was my first academic publication at the workshop in the Benelux. So it was my first paper ever, with an audience of 10 people that were yawning all the time. So yeah, they were mostly interested in coding theory, and I was just there. Yeah, but it's quite an interesting mapping, and yeah, I think it's the best thing you can do. So as far as S-boxes, as far as nonlinear mappings in symmetric crypto are concerned, this is the best you can do. That's what I think. Okay, so we're going to use these things with keys. So Ketje, Kiak are keyed functions, but also the other are keyed functions. So we want to protect against side-channel attacks, more in particular DPA, DEMA. So we have here again our expression, but now without loss of generality, we just don't write I and I plus 1, but to make it simpler, we just look at the first bit. Yeah? So the first bit depends on, at the output, depends on the 3 first bits of the input. And we're going to represent, we just use masking, and we're going to represent each bit as a sum of 2 bits, where the first part is completely random. So we generate it randomly, and we generate the second part by just subtracting xi. So by themselves, ai and bi are completely decorrelated from the native value. So this I call the native value. And what we're now going to do is we're going to work separately on ai and bi through the whole computation. So what does this look like? Well, we just fill in this ai plus bi everywhere we have xi, and then we pull it apart into an expression for computation of A0 and B0. Yeah? So what you see here is that's pretty safe, because we do all computations for A0. It's all on those of share A, but share A is completely decorrelated from the native value. So this is safe, and this is all on B, except here this last term. So that's a bit of a problem, because if these two, A2 and B2, meet somewhere during the computation, if we happen to have an intermediate result that contains both, A2 plus B2 is equal to X2. So you get a correlation with X2. So we want to avoid that. We can do that in software by doing really good scheduling and implementing an assembly and making sure we don't overwrite the register where was A2 with B2 and so on. But in hardware, it's much harder because we don't know about the propagation and you have these glitches. So we want to solve this. Yes, I should say this is something we already published in 2000. So we have a step of 10 years between our G and our first masking of G. But it's quite long ago. That was before was announced at Rijndal 1 AES. So we were already working on bit slice ciphers at that moment. Okay, so what we can do is to try to avoid it, see if we can pull it off with 3 shares. So in this case, we generate AI and BI randomly and compute CI as the sum of AI, BI, and XI. So any set of 2 shares is independent of the native value. And now we're going to do the same trick, and we're going to compute separately on AI, BI, and CI. Not really. But what we try to do is in each computation of each output, only use bits from 2 shares. So 1 share is not present. So this means that, for instance, the computation of A0 is completely decorrelated from XI, from the native value. So that works very nicely, and this is something we published again 10 years later at the second SHA-3 conference. It was in the context of SHA-3. So we did not invent this, of course. This is clearly based on these threshold masking schemes that were proposed by Svetla, Vincent, Christian, and Martin. And this is a general schematic. So, and they proved that this scheme here computes this in a way that is secure against first order DPA, if this satisfies a number of conditions. So the first condition is correctness. Basically, if the sum of the x's here equals x, then the sum of the y's here must equal this y. Yeah? Of course, that's a trivial property, otherwise it's not even correct. And the second property is incompleteness, saying that each of these separate computations of an output share must depend on at most, well, depend on at most all input shares minus 1. So there must be in this input 1 share should not appear, and that's the case here. So for YA, it takes only as input XB and XC, and so on. So this can only be done if this is done in 3 shares. Actually, the number of shares is determined by the algebraic degree of this function. So if the algebraic degree of this function we call D, I think it's a conflict with the previous talk. That's a different meaning of D, so I should have chosen another letter, but it's the D of degree, so it's quite, it was quite natural. But anyway, if the degree of this function is 2, we can take 3, but if the degree is, for instance, 5, we have to take 6 shares. So that's really determines how expensive it is, because it's not cheap. So you have to triple your state, and your computation is times 3, even more. Yeah? So it's really quite expensive, but we get some kind of nice guarantee that we are secure against first order DPA, and if we then boost the noise, we think we're safe. So a third condition is not so much on this functions f, but on the input variable. So the input variable, this xa, xb, xc, should be a uniform sharing of this native value x. So that means that actually all possible values xa, xb, xc compatible with x, so for which their sum is x, should be equiprobable. Given here an example for a single bit. So if x is a single bit equal to 0, then this xa, xb, xc has 4 possibilities, namely all those where there are an even number of 1 bits, and these are an odd number of 1 bits. And these 4 have to be equiprobable, which means for the adversary, he must have no information at all on which it would be. So total uncertainty. Okay, so that's it. That's nice. But we have one more property of the function f, of the sharing f. So we want to do iterated computation. So we want to do this. This is typically a round function, and we do it multiple times. And if this is uniformly shared, this doesn't leak. But we did not say that this is uniformly shared. So we want actually that this sharing, FA, FB, FC, preserves uniformity. So if this is uniform, then this should be uniform. And that's a property of F, so it preserves uniformity. So that's not so easy to express, and not so easy to understand in general, but if F is a permutation, so if F is invertible, then it's easy to understand because it's equivalent to this being a permutation. It's equivalent to being able to compute backwards from here to here. Yeah? That's it. Okay, so back to our Chi prime, so the sharing of Chi with 3 shares, which we made up in 2010. That was 4 years after this paper. So, yeah, very nice. So you would think it's okay. Was it correct? Yes. Well, you can easily work it out, and it's correct indeed. Is it incomplete? You can see it's incomplete. Was it uniform? Yeah, of course it was uniform. Maybe, yeah, because how could that not be uniform? But yeah, then we looked. Oh, yeah. So it wasn't. So it was not uniform. So we thought it was uniform, but we didn't understand the uniformity property. Yeah? We never understood it, and we thought it was uniform. So there we had to fix it. And we were not alone. So in fact, there are many S-boxes for which, of degree D, for which no uniform D+1 shared threshold scheme is known. So that became an active research area, and many papers appeared, so saying, yeah, we got a new way to do it, and we're getting closer. And so there's a lot of publications came from that. Okay, so then we set out to try to fix this problem. And there were several attempts, and they all follow a bit the same idea. So first, so we have our S-box. First, we build a correct and incomplete sharing of the S-box. So that's, if the degree is 2, it's straightforward to do. Actually, it's straightforward to do for any degree. You can do that with D+1 shares. Yeah, it's easy. That you can even automate that. Then, we mask the output here with 2 additional shares, which we call RB and RC. That are supposed to have a uniform distribution. So it's kind of a fresh mask we get from somewhere. And you see that RC is added to share A and share B. RB is added to share A and share C. So first of all, it does not affect correctness, because if we take the sum of these 3, these cancel out, because we add them in 2 places, right? You see that, huh? Yeah. Incompleteness is also preserved because we call this a part of C and a part of B. So still, A only depends on BC, B only depends on AC, and C only depends on AB. And the output becomes a uniform sharing of Y. Why is that? Well, if you take, for instance, these 2 together, it's completely random because of Shannon. We add here 2 random values, so this is completely random. But these 2 together are also completely random, and these also completely random. So this is, in fact, this output is fully uniform. Okay, this costs a lot, but the smart trick is we can chain this. Huh? So for the next S-box, we put our S-box in a long line, and for the next S-box, we just take, as these random values, the input shares here, the 2 input shares, so B0 and C0. We just add them here, and here B1, C1, and so on. So that's it. So we only have to deal with this. Yeah? But where do these come from? So these are the different approaches. This is not new. Huh? So the first attempt was, okay, we're just going to every round inject fresh randomness. Huh? So if the S box is, let's say, 4 bits, this is generic. This is not only for G, this is completely generic. If the S box is 4 bits, that requires 8 random bits per round. So if you look at what people are trying to do with AES S box, this is quite modest. So only 8 bits per round. What are the disadvantages? Well, in a real-world implementation, you have to have this random generator on the chip and generating randomness on the fly. And academically, you cannot get this published easily because there's not really, you cannot claim this is a uniform sharing. Yeah, it solves the problem maybe, but that's not an academic achievement. Still, it was presented, we did it in a paper that we did with some COSI colleagues, and it was one of the countermeasures we proposed together with others to fix the problem in Kedjak. Okay, then second attempt. Very simple. Here at the end, we are not using these last ones of the last S box, the rightmost S box. So what we're going to do is we're just going to recycle them. Let's assume this goes in here and comes back here. We're just going to use them here. Yeah, that's very smart. Now we don't need any randomness anymore. So this is this works. So I investigated it, and actually you can show that the remaining amount of non-uniformity is so small that you cannot exploit it in an attack, which means that the higher order attacks will become more efficient than this one. So it will be less efficient. The first order attack is in principle not excluded, but it's less efficient. So I tried to convince the world of that. Nobody bought it, actually. And academically, it's not uniform. So you cannot say it's uniform because it isn't. There's still some non-uniformity. It's very small, but you cannot. So I toured the world with this for a while. I gave first presentation at Shonan, I think now exactly 3 years ago, and a few more times. And I think FX was at all 3 presentations, and he always said, yeah, but it's not right. So I could not convince the people. Okay, so then finally, at some point I thought, we can do this. And it's very simple. It's just, instead of here, these two, recycling or throwing away, we make it part of the state. We make it part of the shared state. So we consider this an extension of share B and share C. And we call this the guards. And whenever we do a round, we do a nonlinear layer, we take these values we still have lying around here at inputs, and that's what I call the change of the guards. So that's where the title comes from. So I can show that this achieves uniformity if the S box is invertible. I will do that on the next slide, and that will be then probably my next slide. How much time do I still have? 3 minutes, yeah. So I can prove it in 3 minutes. I have to prove it in 3 minutes. The cost of this is, here we have these XORs, so it's only 4 additional XORs per native bit. And the extension of the shared state is with two shares of S box width. So the proof is simply the following. We just have to show that this is invertible, and we do that by giving an algorithm to compute this, so the input from the output. So let's see if I can still reconstruct it. We have these two, the guards. The guards are equal to B2 and C2. But we know A2, B2, C2. We know the corresponding Y. But the S box is invertible, so we find the corresponding X. So we now have here the native value and 2 shares. So we compute the third share from these two shares and the native value. See that? Then we have all 3 values here. And we know the input to this. We know the input to this. So we compute this mapping and this mapping. And from these two, we can compute this, this in between. And from these two, we can compute this in between. What is added? So what is added is basically C1 and B1. So we have here found A2 and also B1, C1. And then we can continue this until we're here. So it's a very simple algorithm. So this shows that this is a permutation, so it's invertible, so it's uniform. So that's basically it. So there is an optimization trick specific for G prime, where basically we can reduce this to not full width of the S box, but only 2 bits. So I'm not going to explain it because I don't have the time. I took too much time. I also have a slide generalizing this to D-share, so it's not really important, but it helped in getting the paper accepted because it's generic. So, conclusions. I've given a solution for achieving uniformity for invertible S-box layers. You can do it with D, which plus 1 shares, where D is the degree of the S-box. The uniformity is achieved outside the S-box. So you don't do it at the S-box level, but outside. So in the real world, the sharing of Ketchak is made uniform at little overhead. Academically, the non-uniformity problem is essentially solved, I think, so you can no longer publish about that. But what you can look for is ways to optimize it for other S-boxes by looking for the same property that we have in Xi in Ketchak. Thank you.
Thank you for the talk. We have time for a short question. No, if no, we can thank the speaker again. The last talk of the session is generalized polynomial decomposition for S boxes with application to side-channel countermeasures, and the talk will be given by Dahmun Goudarzi.
Thank you, Emmanuel, for the introduction. So first of all, a little bit of background. In this work, we are in a context when we want to securely implement in software a block cipher protected against side-channel attacks. For this purpose, we use a common countermeasure, which is the higher order masking, where you split every sensitive variable x in the cryptographic computation into d random values, not the same d as before, such that the sum of all these values is equal to the sensitive variable. This is a sound countermeasure since it has been formally proved that the more the masking order d grows, the more it is exponentially difficult for the attacker to recover any information about x. However, when you want to implement this in software, working with mask variable has a cost. Linear operation are linear in the masking order, but the nonlinear operation are quadratic, and this implies a cost in time and memory. Therefore, the main goal is to find efficient ways to implement the nonlinear operation, namely to implement the S-box, and find a representation of the S-box that has a minimum number of nonlinear operations. To solve this problem, there is several approaches in the state of the art. One of the main is to look at the S-box as a polynomial over a final field f to the power n, where n is the input of the S-box. You have two problems. Either you want to decompose generic S-box, so any random S-box, and you will look at it like this. And the two main solutions proposed is the CRV decomposition where the nonlinear operation are secure field multiplication, and the algebraic decomposition, where the nonlinear operation are composition of algebraic 2 functions. Another problem is to look at specific S-box, since their S-box has structure, and for example, it is well known for the iOS that the polynomial representation of the S-box can be seen as x to the power 254, composed with an affine transformation. For this problem, the two main solutions, the best solution in the state of the art, are the RP multiplication chain that consists in 4 secure multiplication on f2 to the power 8, and the KHL multiplication chain that use one more multiplication but on a smaller field on f2 to the power 4. Another approach for this is what we call the bit-slice method, where you no longer look at the S-box as a polynomial, but as a Boolean circuit to implement it in software with bit-slice. So the S-box can be seen as m-coordinate function, where each of these coordinate functions is a Boolean function. For the generic method, this is similar to the polynomial method, but now you have work with Boolean function. And for the specific method, for example, for the IS, you try to find the most compact circuit that will evaluate this S-box. And for this, the circuit from Boyer and al. use only 32 nonlinear gates. How does these two methods compare in practice? So we implemented this for generic 8-bit SBox on ARM 32-bit assembly, and we can see that for small masking order, the polynomial approach are better, but the bit slice method are asymptotically the best. But these two cases are kind of extreme. In the polynomial method, you work on the full field, and on the bit slice method, you work on the Boolean field. What will happen in terms of performances if you work on intermediate field? So yes, you have the full field, the Boolean field, intermediate field. For example, for 8-bit SBox, the median case will be where you represent the SBox as two coordinate functions that work on 4-bit elements. This is motivated by the fact that, for example, for the IES, it performs very well for several reasons, but one of them is, for example, when you implement this on a 32-bit architecture, the smaller the elements are, the more you can pack them into a register to perform them in parallel. For example, you can do, for the Boolean case, 32 multiplication in parallel. With 4-bit elements, you can do 8 of them in parallel. And for 8 bits, you can do only 4. And in terms of performances, for example, to evaluate the SBox of one round of the IES, the KHL method, which used 5 multiplication on F2 to the power 4, is for any masking order faster than the RP decomposition method that had one less multiplication, but on F2 to the power 8. So in this work, we propose the generalized decomposition method for any SBoxes that is instantiated with 3 parameters: n, the number of inputs; m, the number of output element of your SBox; and lambda, the bit size of your element. And now you can see, and then we studied the median case. So as I said, for 8-bit SBox, for example, you have two coordinate functions, f1 and f2, that works on 4-bit elements. And finally, we did an implementation on 32-bit architecture to compare it with the rest of the state of the art. So how does this generalized decomposition method work? So now you will look at the SBox as a n lambda bit to m lambda bit polynomial over the field f2 to the power lambda. So the SBox can be seen as m coordinate function fi, where each of these fi belongs to the set of functions from f2 to the power lambda power n to f2 to the power lambda. How to decompose a single coordinate function? So you look at the coordinate function, you represent it as the sum of t plus 1 product between the gi and the hi. How to generate such decomposition? You will pick the gi as random linear combination from a basis. So what does this mean is the basis b bar, the span of the basis b bar simply means that this is all the possible function you can reach with linear operation. So if you have a basis b of function phi, this is all the possible linear combination that you can obtain, since squaring is free with mask variable because you work on a field of characteristic 2. Once you generated such a polynomial, you need to find the coefficient of the hi under its representation with this basis by solving the following equation, where you evaluate the coordinate function on every point. How to solve this equation? You will look at it as a linear system, where the I are all the possible vectors on f2 to the power lambda power n, and you rewrite it with linear equation, where the I are matrix of none, and the ci are the coefficient you try to recover, and the right hand part is all the possible evaluation. In order to have a solution for this linear system, you need some condition on your parameters, but you also need to be able to reach all possible functions because you want to have a generic method that works for any SBoxes. So what are those conditions? You have t plus 1 times the cardinality of the unknowns, 2 to the power n lambda equation. Therefore, you need this inequation to be satisfied in order to have a solution. This means that for a chosen basis, you have a condition on the number of decomposition product that you need, which is the following one. It is interesting to notice that the bigger the basis you will pick, the smaller decomposition product you will need for each coordinate function. And finally, in order to be able to reach every possible function, you need that all the product of elements in the basis B spans the span of this spans the entire space of possible functions. This condition can be seen as what we call the spanning property, where this is equivalent to you construct the matrix of all possible products in your basis, and if this matrix is full rank, then your basis B satisfy the condition that you need. How to generate such bases? You will first start with all possible monomial plus the constant one. You pick two elements in the linear power closure. You multiply them together. You compute the new rank. You repeat this process an arbitrary number of times, and you will pick the pair that increase the most the rank, and you reiterate this until you have a full rank matrix. Like this, you will generate what we can call random bases. And actually, using random bases is better for some previous work where they used arbitrary bases with specific structure. For example, for the Boolean case, we are able to reduce the number of multiplication needed to compute the bases from 25 to 7. Here are some results for 4-bit Xbox and 8-bit Xbox, but in the paper you can find them for all kinds of Xbox size. And now that we know how to decompose a single Boolean function, coordinate function, sorry, to decompose the S-box, you simply need to apply this coordinate function decomposition on each of the coordinate functions. We add an improvement that is called the basis update. How it works, you start with your initial basis, you decompose the first coordinate function, so you obtain a certain number of products that you computed, and you can add them into your basis to do the next decomposition, and by doing so, you will have a bigger basis for the next coordinate function, and you will reduce the number of decomposition products that you need, if you recall the condition on T. A small example, so for example, for a random 8-bit S-box, if we pick the parameter n equal to 2, m equal to 2, lambda equal to 4, so the S-box can be seen as two coordinate functions. You generate a first basis B1 that satisfies the spanning property. You decompose the first coordinate function by picking the G1 functions into the basis B1 and find the coefficient of the H1 by solving the linear system. Then you will get T1 decomposition product that you can add into the basis B2, and you will decompose the next coordinate function by picking the G2 into this new basis. Now let's have a look at some results. So first of all, what is the cost of this decomposition? So first you will need R multiplication to generate the basis B, the initial basis, plus the sum of the TI for each decomposition product, and your TI must satisfy at each step a condition that is dependent of the size of the basis. And the optimal parameter are actually achieved when TI is equal to this value. But in practice, you don't always achieve optimality. Small example on 4-bit and 8-bit S-box, but you can find more in the paper and for several set of parameters L, lambda, and n. So for 4-bit S-box, if you work on element of 2 bits, you have two inputs. The initial basis will have 5 elements, so this means that you need 2 multiplication to generate it, and then each coordinate function is generated with 1 product, which makes a total cost of 4 multiplication, and this is equal to optimality. For 8-bit S-box, for example, for the median case, where you have 4-bit elements and 2 inputs, you need an initial basis of 10 elements, so you have 7 multiplication to compute then. The first coordinate function needs 7 multiplication, the second one 4, and at the end you have 18 multiplication, which is 1 above optimality. We did an implementation of this on 32-bit architecture. Unfortunately, for timing, we were not able to beat the other method, but we have a trade-off with the memory where we have less memory requirement. Finally, in this work, we did a generalized decomposition method that is well suited for any S-boxes. What we did actually is close the gap between the Boolean case and the full field, where we did all the possible field in between, and we also did an extension to work on bigger field, where the size of your element doesn't necessarily divide the input or the output of the S-box, and this is based on the paper from Srinivas last year at CHES. And and also we did a case study on a 32-bit architecture, an implementation comparison with the state of the art, and we can find memory trade-off. And this can be well suited for low-end device, since the smaller your architecture is, the less poorly will bit size perform, and it has few memory requirements. So this can be well suited for low-end device. Thank you.
Thank you for the talk. We have time for questions. I have one question. Do you have lower bounds for the number of multiplications needed to compute the bases?
The bases?
So you achieve on slide 17?
Yeah. We do, but yes, we have one in the paper, but in practice we don't necessarily achieve it because we need to be able to decompose everything. And
so what is the lower bound, for instance? So you achieve 17?
Recall the formula. We have one in the...
Okay.
Yeah.
You have one in the paper?
Yeah.
And you have no idea about the tightness of the bound?
Like this, no. I'm for 8-bit, it's 14. I remember, but
okay. Question. Last question. You succeeded to improve the previous methods by working on subfields. Yes. Do you think that we could look at the other direction? So improving the method by going into larger fields.
That's what Srinivas did in last year, and we also generalized it for bigger field, and this can be found in the full version. But yes, and actually this is interesting because you are more tight on your equation, for example, since you can discard the equation in the system that you don't need. You can play with what output you take. For example, if you have an 8-bit box and you work on 5-bit element, you will have 2 input, and then you will project your equation on F2 instead of F2 to the power lambda, and then you can be more tight in what you do because you can discard. If you have wrong drops and stuff like this, you can do it, whereas it's more difficult here.
Okay. Thank you. No question? So we can thank the last speaker. So thank you, everybody. We can thank all the speakers of the session, and it's time for a pause.